Hello, this is Seth Schaefer from Team Just Cause Robotics, and today's video will be a bit more experimental than usual. You see, the past month or so I've been on a quest. This quest is one I have chosen knowing it will be a challenge, yet it is one I wish to see through. I am well aware that having an angled bar spinner on a robot causes a lot of problems, and my goal is to find the simplest, cheapest, and most reliable solutions to those problems. This is my quest. I will know I have completed this quest when Mini Mulcher is capable of lasting 3 minutes in a fight, driving around with full control of my own actions with at least 50% speed on the weapon, and on top of this, it must be able to get up when knocked down by righting itself back onto its wheels. It must not rely on any lucky bounces off the walls or hits from its opponents to do so. In fact, it should be able to right itself even from unfortunate positions like in a corner or against a wall, and maybe even propped on its side. So, to recap, my goals for Mini Mulcher are 1. Last 3 minutes. 2. Remain drivable at 50% weapon speed. 3. Self-right reliably. And 4. Never lose to itself. Number 4 is mostly referring to my bot being able to break itself and losing a fight purely due to its own actions. Even some of the very early versions of Mini Mulcher could accomplish the first of these 4 goals, but all have struggled with the others to some extent. The drivable ones weren't able to self-right, and the self-righting versions have trouble with 2 and/or 4. My last Mini Mulcher video showed version 0.8 in gray PLA destroying stuff. It was pretty stable, but because it had no rating system at all, it was easily able to defeat itself by flipping over. I split off another version 0.9 in CAD, which was very short-lived, the main difference being a new front fork attachment which uses just 2 forks instead of 4, and it weighs half as much, giving me an extra 20 grams or so to dedicate to a righting arm. That ended up with its own flaws, however, so I beefed it up later on. I then began to experiment with righting poles. This is something we'll be doing soon for Bloodsport as well, making this an opportune time to discuss the design process for such a device. Let's back up for a sec. There are 3 ways to prevent your robot from losing by being turned upside down. Number 1. Make the robot drive inverted. Number 2. Design special bot geometry, letting it right itself with its weapon and/or drive systems. Number 3. Add a separate powered StreamX system that's only meant to flip you over. And secret option 4, YOLO, better not get flipped. Almost a year ago, I asked builders which they prefer. I asked with many other more granular options, but they all fall into one of the 4 categories. Here are their responses. You can see pretty much the last thing most builders want to do is dedicate weight and mechanical complexity to a StreamX. The most elegant way to deal with the problem is the most obvious, invertibility, but that isn't possible for most weapon types. I chose to attack the problem the same way as Bloodsport will, using a self-righting pole of sorts to roll Mini Mulcher back onto its wheels using the weapon. Simple, right? Wrong. This brings me to a concept that I have decided to call the self-righting Triforce. Through trying to design and test a righting arm, it became readily apparent to me that I was pushing the tiny 2204 weapon motor to its absolute limits. This brings us to the first part of the Triforce, torque. When I was searching for a motor for Mini Mulcher, I immediately discounted that I could use anything over 2000 kV because that would make the top speed of the weapon much too fast. I was worried about wasting weight and space on needing a bigger gear reduction to keep the top speed manageable, and I'd already decided on a 26:10 ratio, which I'm using now. What I failed to realize was something that was brought to my attention when researching my drivetrain guide videos, and that is the true relationship between brushless motor KV and torque. I knew that generally with a given motor model, the higher the KV, the higher the stall current, and thus the better power to weight ratio. But I'd forgotten that the greater the ratio of stall current over KV, the greater the torque constant for the motor, meaning not just more peak torque, but actually more torque per amp. This meant that by stepping up to an ever so slightly larger 2205 motor, which was rated for 2300 kV, I was able to get nearly 1.5 times the torque per amp. And with a higher stall current of 22.5 amps versus the 13 amps of my 1960 kV 2204 motor, this 2300 kV motor has over 2.5 times the peak torque. I quickly ordered the 2205 motors, and as soon as I got them, I threw them into the Mini Mulcher V0.8 chassis. I then ran into a bunch more problems. I wasn't recording at the time, but with no lid or weapon on the robot, my first attempt to spin up the 2205 motors resulted in smoke pouring out of the bot. A couple of hours of troubleshooting electronics and rewiring my battery connector let me finally spin the motor up, but there were more issues. The screws that came with the 2205 motors were longer than those that came with the 2204, and the base plate is also thinner, so even the 2204 motor's shorter screws were compressing the coils in the new motor, causing it to violently buzz instead of spinning up, even though the shaft would spin freely. Running it with a bit looser screws, I was able to do a couple tests, but it was pretty unreliable. I was also generally sick of using a link. I've always preferred switches for ease of use. Having the link fly out from how fast the chassis could spin, and potentially having it knocked out during a fight was also a silly risk to take. Plus, it was a nightmare to wire up due to all the tight bends and the forced right angle, and it took up tons of space. With hardly any room for wires, the lid would bulge up every time I put it on. After searching through my toolbox, I found a spare fingertech switch I had bought for Division, and it seemed like the obvious ideal solution. A couple hours in CAD later, and 5 or 6 hours on the printer, version 0.10 was born in bright red PLA. Another, much more pleasant soldering session later, I was left with a much cleaner internal wiring scheme. So now for part 2 of the Triforce, balance. Balance refers to where the center of gravity ends up with the bot in various orientations. In order to flip a robot onto its wheels, it needs to get to a tipping point where the center of gravity is on the side of the wheels. Once the center of gravity is on the side of the wheels, it will tend to fall onto its wheels. This is really hard to explain in words or even demonstrate with the CAD, so I'll show you on the actual robot. Alright, so to try and explain how the self-righting Talon, or any kind of self-righting system, is supposed to work on this robot, you have to understand basically the balance and leverage aspects of the triangle that I mentioned earlier. So by balance, what I'm referring to essentially is where is the center of gravity of the robot. So if you're talking about vertically, if I balance the robot on like my finger, it tends to tip towards the weapon side unless I get pretty high up. So the center of gravity is right around here, kind of like about at the level of the lid of the robot, near where the weapon shaft is. So basically this means if I put the robot like this, because the center of gravity is over here instead of over here, it naturally will fall upside down, which is bad. When it's like this, the center of gravity is between the wheels, so it's fine existing like this, but at a certain angle, it will naturally want to, only at a certain angle will it naturally want to fall onto its wheels. So it needs to be at roughly this angle before it will want to fall onto its wheels. If I tip it anywhere past that angle the other way though, now it will fall onto the weapon side because it's heavier on that side. So the problem is that when it's like this, it'll still naturally fall to the weapon. So I need to push it beyond that angle. How I do that is with this like curly Q righting Talon thing. So how this works is the robot needs to use its weapon to get leverage to tilt itself up. So the weapon only spins in this direction, remember. So if it's on the ground like this or like this, it will spin. The weapon can bite into the floor because it's much harder than the floor, and it will probably end up in this orientation one way or another. Whether it starts out this way or it's over here, the weapon trying to turn will eventually get it into this position. Once it's in this position, the weapon's still going to bite into the floor. So I'm going to turn the robot with my hand to simulate the weapon being driven into the floor. And I'm kind of planting this point in the floor to show that, because the robot sliding on the ground with a slippery nylon chassis is a lot less friction than the point of the weapon driven into the floor. So as I turn this, you can see, maybe you can see it better this way, that Talon is curling up underneath, and it's tending to rotate the robot onto its side. So if all I do is rotate it, it kind of naturally ends up at this position. And then if I keep going, eventually it gets past that balance point and tips back onto its wheels. So that's the idea behind how I get this to work. So the weapon needs to have leverage to get it to the point at which the robot can then balance on its wheels again, instead of balancing upside down. And it's sometimes difficult to get that. This thing is maybe a bit shorter than it should be, ideally. So it's kind of iffy to get to that point. You can see that if I'm not super careful, once I get here, if this weapon is sliding instead, and the robot is kind of pulling the weapon along, it will actually end up back upside down. But if the weapon is stuck into the floor, then it can get back to the angle that it needs to. In that clip, I kind of minced my words about leverage. Basically, the reason that the Talon is curved is to allow the bot's weapon to have consistent leverage, the third triangle of the Triforce. If it were a straight angled pole like on Gigabyte, weapon system would need to work super hard at the start of its rotation when there's very little leverage to begin raising the bot's mass up higher, and towards the end, it would need to work much less hard as its leverage increases. This is because the lever arm is effectively much shorter just as it's starting to raise up, and much longer as it is finishing being raised. Making the motor work harder at the start is bad because it can lead to a stall condition, especially when the battery is low. By curving the writing Talon, it acts more like a screw than a lever, making the amount of leverage more consistent throughout the action of raising the bot's center of mass off of the ground. Now, we have understood and acquired all three parts to make up the Triforce. So, testing time again. As is so often the case, I entered a cycle of build, test, fix, repeat. I began with a kind of flat flower petal design, but this failed to ever get the bot onto its side since the two petals were a flat surface it could sit on. I tried snipping off a petal, but the flat design just wasn't cutting it. I then designed an angled curved Talon with a 30-degree slope. This had mixed success, so I moved on to a 40-degree slope, which is what I'm using now. With some mixed success, I found that the brittle PLA writing Talons broke way too easily. I switched to nylon, which is the latest version you just saw. This is very close to perfect. It just needs a few more tweaks and I'm sure it'll be great. Then, of course, the entire chassis broke due to the sideways shock from too hard of a hit. It turns out that the force path in my robot's chassis is such that basically all of the load from any sideways hit is taken up by the lid and the base plate of the chassis. And the lid's actually even thicker than the base plate, so the base plate is the real weak point there. I reprinted the entire chassis in nylon, including the lid, and now I just have intermittent stability issues, in part due to the flexibility of the nylon. The flexibility of nylon is why it's so durable, but of course it has its downsides. You can see here, the top panel is now flexible enough to allow the forks to escape, so I'll have to extend the front of the lid. Nylon is also a lot softer than PLA. Due to this, I also accidentally stripped out the printed threads for the shoulder bolt weapon axle in my new nylon chassis, which I had never done before with the PLA versions. This caused a whole host of new issues. Firstly, there were extremely inconsistent instability problems, even at much lower weapon speeds like 15 to 20% or so. Likely this is due to the weapon having too much vertical play because I can't clamp down on it all the way. So when it stops accelerating and being pulled in one direction by the helical gear forces, it can start to resonate up and down and it'll cause it to flip out even easier. This also may be a case of pull load instability, but why it's now suddenly happening at less than half the speeds I could achieve before is beyond me. Second, the writing Talon can spin around without any real torque on it, so it can be turned in front of the robot where it's useless for writing, as I showed earlier. So to recap, Mini Mulcher is getting much closer to reliably self-writing. Stability is still an issue which probably needs a more rigid weapon system to address. The electronics are much cleaner and wiring is much easier. Wire runs are shorter, and there's less internal space for them all. The bot now uses a finger tech switch rather than a link to power on and off, which is a far more bulletproof solution. So what's next? I'm going to make another design change to add a nylock nut that retains the shoulder bolt for version 0.11, but I just ordered the nylocks and won't have them until next week, so hopefully I'll have better news then. I also think that the chassis rotating counter to the weapon is mainly an issue due to not having enough tire traction, so I'm looking at making new wheels with a different tread than the O-rings. It should actually be even cheaper than the O-ring solution and nowhere near as complicated as casting silicone tires, but the tire tread I'm looking at using is about a Shore 35A hardness compared with the Shore 60 to 70A that I've been using with O-rings. This might also dampen some of the vibrations, causing it to go unstable as well, but we'll have to test it to find out. Stay tuned for a part 2 video. Thanks for watching. If you liked this video and want to see more like it, make sure to subscribe for more content and hit the like button down below. If you want some sneak peeks before the next video, check out my Instagram linked in the description.